In question 1, we're given the equation of the curve C, and we need to find the equation of the tangent at the point 2, 3, giving our answer in the form ax plus by plus c is 0, with a, b, c being integers. Well, we need to apply implicit differentiation here, which means we differentiate from left to right. We apply all rules as usual. If we happen to be differentiating a term in y, then we put a dy dx term as well. So on the left hand side, we've got xy squared. So I'll be applying the product rule of differentiation. I differentiate x, I get 1, and I keep the y squared. And then I differentiate the y squared and I keep the x. So we're looking at x times 2y dy dx. And this is equal to 2xy plus x squared dy dx. And the derivative of 6 is simply 0. I will now substitute x is 2 and y is 3. And I will solve for dy dx to get the value of the gradient of the tangent. So we're looking at 3 squared plus 2 times 3 dy dx being equal to 2 times 2 times 3 plus 2 squared times dy dx. So we've got a 9 plus 12 dy dx being equal to 12 plus 4 dy dx. So on the left hand side, I'm having 8 dy dx being equal to 3, and therefore we conclude that dy dx is equal to 3 over 8. We can then recall that the equation of the line is given by y minus y1 is mx minus x1. So we're looking at y minus 3 is equal to 3 over 8 times x minus 2. I will cross multiply by 8, so I will multiply y minus 3 with 8, leading to 8y minus 24 being equal to 3x minus 6. And if I collect everything on the left hand side, I get 8y minus 3x minus 18 is equal to 0. In 2a, we need to find in ascending powers of x the first 3 non-zero terms of the cube root of 1 plus 4x to the power of 3. So we've got 1 plus 4x to the power of 3 and its third root, which I will write as 1 plus 4x to the power of 3 raised to the power of 1 over 3. We're looking for the first 3 terms. I will be applying the binomial expansion here. So we start with 1 plus a third, which is the power times 4x cubed, plus a third. I will deduct 1 from the power, taking me to minus 2 over 3 over 2 factorial times 4x cubed raised to the power of 2 plus dot dot dot, which simplifies to 1 plus 4x cubed over 3 minus 16x to the power of 6 over 9 plus dot dot dot. In part B, we need to use the expansion we just obtained, substituting x is 1 over 3 to obtain a rational approximation for the cube root of 31. Well, let's start by substituting x is 1 over 3 into the expression we were given. So we've got the third root of 1 plus 4x cubed. I'll be substituting x with 1 over 3. So we're looking at 1 plus 4 times a third raised to the power of 3. And we've got the cube root of this, which gives an answer of the cube root of 31 over 3. This means that if we substitute x is 1 over 3 into the first 3 terms we obtained in part A, we will be obtaining an approximation for the cube root of 31 over 3. So we've got the cube root of 31 over 3 being approximately 1 plus 4 times a third raised to the power of 3 over 3 minus 16 times a third raised to the power of 6 over 9. Well, if I evaluate the right hand side, we arrive at the cube root of 31 over 3 being approximately 6,869 over 6,561. And if I cross multiply with 3 to isolate the cube root of 31, we arrive at the third root of 31 being approximately 6,869 over 2,187. In question 3, we've got the curve C described parametrically here. T, the parameter, varies between negative pi over 2 and pi over 2. and we need to show that the Cartesian equation for the curve C is y being equal to 12 over 7 minus x times 1 plus x, with x being between P and Q and P and Q being constants to be found. Well, let's start by recalling that x is 3 plus 2 sine t, which means that x minus 3 is equal to 2 sine t, and therefore x minus 3 over 2 is equal to sine t. Well, we've got that y is equal to 6 over 7 plus cos 2t, and let's recall the double angle formula for cos of 2t, which says that cos of 2t is 1 minus 2 sine squared t. So the idea here is to express y in terms of sine t and then get sine t substituted with x minus 3 over 2. So we're looking at y is equal to 6 over 7 plus 1 minus 2 sine squared t, which of course gives me y is 6 over 8 minus 2 sine squared t. Well, I will divide everything by 2 to get 3 over 4 minus sine squared t, and I should be able to recognize the denominator, the 4 minus sine squared t, as the difference of two squares. So we're looking at y being equal to 3 over 2 minus sine t times 2 plus sine t. So now it's the time to substitute here sine t with x minus 3 over 2. So we're looking at y being equal to 3 over 2 minus x minus 3 over 2 times 2 plus x minus 3 over 2. So I will multiply everything by 2. So the 2 here will become 4. These will also become 4. And since both brackets are over 2, this means I can get a times 4 here and get rid of the denominators within this denominator here. So we're looking at y being equal to 12, the 3 times 4, over 4 minus brackets x minus 3 times 4 plus the x minus 3. So let's proceed in simplifying the denominator. We've got y is equal to 12 over the 4 minus the negative 3 will give me 4 plus 3, which is 7. So the first bracket is 7 minus x, and the second bracket is 1 plus x. Now the only thing missing is for me to find the values of p and q. Remember, x is between p and q, so I will be substituting the limits for t to find the corresponding limits for x. So let's see, when t is negative pi over 2, we get that x is 3 plus 2 sine of negative pi over 2, which gives an answer of 1, and therefore we conclude that p is equal to 1. And when t is pi over 2, we get x is 3 plus 2 sine of pi over 2, which gives an answer of 5, and therefore we conclude that q is equal to 5, and therefore this means that 1 is less than or equal to x is less than or equal to 5. In part B, we're asked to hence find the Cartesian equation for C in this form where A, B, C, D are constants. So essentially we're being asked to decompose the expression we just obtained, the 12 over 7 minus x1 plus x, into partial fractions. So I'm proposing that this can be written as A over 7 minus x plus b over 1 plus x, where a and b are constants to be found. Well, the LCM of this is the 7 minus x, 1 plus x. So I will multiply throughout by the LCM to get rid of the denominators. So we're looking at 12 is equal to a times 1 plus x plus b times 7 minus x. Now this here is an identity, which means it holds true for all values of x. It makes sense to choose a value for x that will make 1 plus x 0. So if 1 plus x is 0, this means I will be setting x is negative 1, and I will therefore eliminate this part of the identity and allow me to find the value for b. So let's see, I've put x is negative 1, which means that we're looking at 12 is equal to b times 7 minus the negative 1. So 12 is equal to 8b, which means that the value of b is 3 over 2. We can also put x to be 7. If we put x is 7, then I eliminate this part and I'll be able to find a. So let's see. Putting x is 7 leads to 12 is equal to a times 1 plus 7. Therefore, we're looking at 12 is equal to 8a, and therefore 3 over 2 is the value of a. And the only thing missing is for me to write down everything together. So we've got y is equal to 3 over 2 over 7 minus x plus 3 over 2 over 1 plus x. Well, if we notice the question speaks about x appearing first in the denominator, so I'll make a small change here because I've got 7 minus x in the denominator here. I will be multiplying top and bottom by -1, leading to y is -3 over 2 over x minus 7 plus 3 over 2 over x plus 1 in order to match the exact same form that the question is proposing. In question 4, we are given a regular icosahedron of side length x centimeters expanding uniformly. This is consisting of 20 congruent equilateral triangle faces of side length x centimeters. The word ikosi in Greek means 20, so it's 20 identical equilateral triangles. So we need to show that the total surface area, capital A, is given by 5 root 3 x squared. So the area is simply going to be 20 times the area of an equilateral triangle of side length x. So I'm using a half AB sine C. So it's a half times x times sine 60. So this simplifies to 5 root 3 x squared as required. We're additionally given that the volume V is given by the expression here, and we need to show that dV dA is 3 plus root 5 times x over 8 root 3. Well, I will start by finding an expression for dV dx, the derivative of the volume with respect to the side length x, which is going to be 5 over 12 times 3 plus root 5, and the derivative of x cubed is 3x squared. Now the 3 with the 12 simplify, leaving me a 4 in the denominator, and therefore dV dx is equal to 5x squared times 3 plus root 5 and all of it over 4. That's the expression for dV dx. Now I will also find an expression for dA dx. I'll be differentiating the expression we just obtained in part A, the 5 root 3x squared, which is going to be 5 root 3 times 2x, which gives me an answer of 10 root 3x. And I will then be applying the chain rule of differentiation. So dV dA is equal to dV dx times dx dA. Now we've got dV dx to be 5x squared times 3 plus root 5 and all of it divided over 4, while dx dA will be the reciprocal of dA dx. So that's going to be 1 over 10 root 3x. Well, let's see. The 10 with the 5 simplify, leaving me a 2 in the denominator, and then the x squared with the x will cancel out, leaving me an x in the numerator. So all in all, we are arriving at 3 plus root 5 times x and all of it over 8 root 3 as required. Now the surface area is increasing at a constant rate of 0.025 square centimeters per second, and we need to find the rate of change of the volume when x is 2, giving our answer to two significant figures. So first of all, the rate of change of the volume means dV dt. Now we've been given that dA dt is 0.025. It's positive because it is increasing, it's expanding, and the dA from part B is 3 plus root 5 times x over 8 root 3. We're trying to find dV dt, which is equal to dV dA times dA dt. Once more, I'm using the chain rule here. Now dV dA is 3 plus root 5 times x over 8 root 3, and the dA dt is 0.025. Well, what I will do is I will substitute x is 2, so we need to find dV dt when x is equal to 2. So this means that we're looking at 3 plus root 5 times 2 times 0.025 and all of it divided by 8 root 3. If you plug this on the calculator, you get an answer of 0.01889 ... which correct to two significant figures is 0.019 cubic centimeters per second. In question 5, we've got a sketch of the curve described parametrically here. T varies between 0 and 9/4 inclusive. We can see that T is 9/4 when we cut the y-axis and T is 0 when we are on the x-axis. Now we are told to show that the area of R is given by this integral here, where K is a constant to be found. Let's start by stating that the area R is the integral of y with respect to x. The limits, I will call them x1 and x2. Unfortunately, we don't have y in terms of x. We've got parametric equations, so we're looking at the integral of y dx dt by dt. So this is parametric integration. Now we can see that at the beginning, when x is 0, t is 9/4, and at the end, t is 0. This means that the lower limit will be t is equal to 9/4, and the upper limit will be t is equal to 0. I will proceed in finding dx dt, and we know that x is 9 minus 4t raised to the power over half. This means that dx dt will be found by getting the power down over half, deducting 1 from the power, so 9 minus 4t to the minus a half, times the derivative of the bracket, which gives me a negative 4. So this simplifies to negative 2 over 9 minus 4t raised to the power over half. So we're looking at the integral from 9/4 up to 0. Y is t cubed over 9 plus 4t square rooted, and dx dt is the negative 2 over 9 minus 4t to the power over half. So these are multiplied together, and then we've got dt. Now the first thing to do is see that the negative sign can be consumed into flipping the limits. So instead of integrating from 9/4 up to 0, I'm now integrating from 0 up to 9/4. We've got 2t cubed in the numerator, and in the denominator, this is a square root, this is also a square root, so I can put everything under the same square root. So we've got 9 plus 4t times 9 minus 4t, and all of them square rooted, dt. And I can take the 2 out. It's 2 times the integral from 0 up to 9/4 of t cubed. And in the denominator, if we expand the 9 plus 40 times 9 minus 40, it's the difference of two squares. It gives me 81 minus 16t squared, and obviously there's a square root here, dt as required. In part B, we need to use the substitution u is 81 minus 16t squared to find the exact area of R. Well, let's start with u being 81 minus 16t squared. The first thing to do is find the u in terms of dt. So du is going to be minus 32t dt, which means that minus 1/32 du is equal to t dt. In addition, I could isolate the t squared term, so we're looking at 16t squared being 81 minus u, and therefore t squared is 81 minus u over 16. I will also need to change the limits from t to u, so when t is 0, we get that u is 81 minus 16 times 0 squared, which is 81, while when t is 9/4, we get that u is 81 minus 16 times 9/4 squared, which gives an answer of 0. I can therefore proceed with the integral. It was 2 times the integral of t cubed over the root of 81 minus 16t squared dt. So let's see, we've got 2 times the integral from 0 up to 9/4. I will split the t cubed as t squared times t dt. I'll keep the denominator of 81 minus 16t squared square rooted. And the reason for doing this is that the t dt term here will be replaced with minus 1/32 du. The t squared term here will be 81 minus u over 16. and then the square root of 81 minus 16t squared will simply gonna be u to the power of a half. I'm trying to translate everything from t to u, so we've got 2 times the integral from 81 up to 0, because the limit of 0 in t got mapped to 81 in u, and the 9/4 got mapped to a 0. The t squared is going to be 81 minus u over 16. In the denominator, I've got u to the half times minus 1 over 32 times du. So the first thing to do is consume the negative sign into flipping the limits here. So we're looking at 2, the integral from 0 up to 81, and then the 16 here times the 32 gives me 512. So in the numerator we've got 81 minus u, and in the denominator we've got 512 u to the half du. I will take the 512 outside of the integral, so this is 2 over 512 times the integral from 0 up to 81 of 81 minus u over u to the power of a half du, which can obviously be written as 2 over 512, the integral from 0 up to 81 of 81 u to the minus a half minus u to the half du. I can then proceed in integrating. So we've got 2 over 512, we've got 81 u to the half divided by a half, and then we've got minus u to the 3/2 divided by 3/2, with the limits being 0 and 81. So we're looking at 2 over 512. Let me substitute the upper limit of 81. So this is 2 times 81 times 81 to the power of a half minus 2 times 81 to the 3/2 divided by 3. Now if I substitute the lower limit of 0, we can see that both of these are 0, so there is no contribution from the lower limit, so minus 0 here. And if I plug this on the calculator, I get an answer of 243 over 64. In question 6, we are told that 3 consecutive terms in a sequence of real numbers is k, 1 plus 2k, and 3 plus 3k. K is a constant, and we need to use proof by contradiction to show that this sequence cannot be a geometric sequence. Well, we know that in proof by contradiction, we always start by assuming the opposite of what we need to prove. So we say suppose not, i.e. k, 1 plus 2k, and 3 plus 3k are 3 consecutive terms of a geometric sequence of real numbers. Well, we know from P2 that if a sequence is geometric, then the ratio of consecutive terms is always the same. So this means that u2 over u1 should be equal to u3 over u2. So in our case, 1 plus 2k is the second term, u1 is k, u3 is 3 plus 3k, and u2 is 1 plus 2k. I will proceed in cross multiplying, so get 1 plus 2k times 1 plus 2k is equal to k times 3 plus 3k. If I expand the left hand side, I get 1 plus 2k plus 2k plus 4k squared, which is equal to 3k plus 3k squared. This leads to 4k squared plus 4k plus 1 is equal to 3k squared plus 3k. I will be collecting everything on the left hand side, leading to k squared plus k plus 1 is equal to 0. And I will proceed by considering the discriminant of this quadratic. The idea is that if the discriminant turns out to be negative, then we can conclude we have no solutions, and therefore this cannot be a geometric sequence. Now the discriminant is b squared minus 4ac, so in our case it's going to be 1 squared minus 4 times 1 times 1, which gives an answer of negative 3, which is less than 0. And therefore we conclude that we have no real solution because the discriminant turned out to be negative. This constitutes a contradiction, and therefore we conclude that the sequence cannot be geometric. In question 7, we're given the design of a doorknob. The shape is formed by rotating the curve shown in figure 4 through a full revolution about the x-axis. The units are in centimeters. We are given the equation of the curve, and we need to show that the volume capital V is given by this expression here, where K is a constant to be found. Well, we know that if we are rotating about the horizontal, about the x-axis, then the volume is given by pi times the integral of y squared dx. Well, in our case, the limits will be 0 here and 4. We are talking about x limits. So from 0 up to 4, I will proceed in substituting y squared. So we've got a quarter times 4 minus x e to the x and all raised to the power of 2 dx. So I will proceed in expanding within the integral. We're looking at 1 over 16. The 4 minus x all squared will give me 16 minus 8x plus x squared, and the e to the x squared is e to the 2x dx. I will take the 1 over 16 out, so this leads to pi over 16 times the integral from 0 up to 4 of x squared minus 8x plus 16 in brackets times e to the 2x dx. In part B, we are asked to find the exact value of the volume, giving our answer in the form P times pi times e to the q plus r, with P, Q, and R being simplified rational numbers to be found. So we need to evaluate the integral of pi over 16 times x squared minus 8x plus 16 e to the 2x from 0 up to 4. I'll be using integration by parts here, so the integral of u dash v is uv minus the integral of uv dash. I will start by setting my u to be x squared minus 8x plus 16, and my v dash will be e to the 2x. This means that u dash is equal to 2x minus 8, while v is going to be 1 over 2 e to the 2x, and I can proceed. V is going to be pi over 16. Now the uv will be x squared minus 8x plus 16 times a half e to the 2x, and I'm deducting the integral of u dash v, so 2x minus 8 times a half e to the 2x dx. The limits are 0 and 4, so I can proceed. We're looking at pi over 16. We've got x squared minus 8x plus 16 times e to the 2x over 2, and then the over 2 within the integral with the 2x minus 8 will leave me x minus 4, so it's minus the integral from 0 up to 4 of x minus 4 times e to the 2x dx. I will apply integration by parts for a second time, this time on the integral of x minus 4 times e to the 2x. So I'll be setting u to be x minus 4 and v dash to be e to the 2x. This means that u dash is equal to 1 and v is a half e to the 2x, and therefore the integral of x minus 4 times e to the 2x dx is going to be x minus 4 times a half e to the 2x minus the integral of a half e to the 2x dx. This gives an answer of x minus 4 times e to the 2x over 2 minus e to the 2x over 4, because I also divided once more by 2, so the half became a quarter, and therefore I can put everything back together for an expression for the volume V. So we're looking at capital V is pi over 16, and within the bracket we've got x squared minus 8x plus 16 times e to the 2x over 2 minus we've got x minus 4 over 2 times e to the 2x minus e to the 2x over 4, and I close the brackets here, and the limits are gonna be 0 and 4. So I have substituted here the result from the second integration by parts. Before substituting the limits, I will simplify the expression, so it's pi over 16 I've got x minus 4 squared times e to the 2x over 2 minus x minus 4 times e to the 2x over 2 plus e to the 2x over 4, with the limits being 0 and 4. Well, let's substitute the upper limit of 4. So we're looking at pi over 16. If I substitute the 4, this will be 0, this will be 0, and then this will simply be e to the 2 times 4 over 4. That's the upper limit substituted. So e to the 2 times 4 over 4. And then if I substitute the lower limit, I've got 0 minus 4 squared times e to the 0 over 2 minus the 0 minus 4 e to the 0 over 2 plus e to the 0 over 4. That's the lower limit substituted. Let's proceed into simplifying things. We are looking at pi over 16, and we've got e to the 8 over 4 minus, in brackets here, 8 plus 2 plus 1 over 4, and we close the brackets so we can proceed into simplifying things. We've got pi over 16, and within the bracket I've got e to the 8 over 4 minus 41 over 4, which means I can take the over 4 as a common factor out, leading to pi over 64, and within the bracket we've got e to the 8 minus 41. In question 8, we are given the position vectors of A and B, and we are told that the line L1 passes through both of these points, and we need to write down an equation for line L1. Well, I will start by finding the vector AB, which will give me the direction of the line. So it's going to be the B, 6, 0, 7, minus the A, which is 6, 6, 2. So 6 minus 6 is 0, 0 minus 6 is negative 6, and 7 minus 2 is 5. So we're looking at the straight line L1 with equation R being equal to the position vector. I can pick either of these two, so I'm just going to pick A, 6, 6, 2, plus a scalar, which I will call lambda, times the direction, which is 0, negative 6, 5. In part B, we're given a second equation L2, and we need to show that the two lines do not meet. So what I will do is that I will be equating the I components and the J components and then the K components. So I've got 6 plus 0 lambda being equal to 3 plus mu, and so on. So this leads to 6 being equal to 3 plus mu. This is found by equating the I components. If we equate the J components, we get 6 minus 6 lambda is equal to 1 plus 5 mu. And by equating the K components, we get that 2 plus 5 lambda is equal to 4 plus 9 mu. Now it's easy to see that from the first equation we don't have lambda appearing, so we can easily conclude that mu is equal to 3, and I can proceed into the second equation to find the value of lambda. So this means that we've got 6 minus 6 lambda is equal to 1 plus 5 times 3. This leads to 6 minus 6 lambda being equal to 16, and therefore minus 10 is equal to 6 lambda, which means that the lambda is minus 5 over 3. All I need to do now is check into the third equation here that the values for lambda and mu yield a true statement. So we've got 2 plus 5 lambda. So 2 plus 5 lambda is equal to 2 plus 5 times the negative 5 over 3, which gives an answer of negative 19 over 3. Now, if upon substitution of mu for 4 plus 9 mu, we get an answer of minus 19 over 3. It means we have validated the third equation, and therefore the two lines meet. And since I've been asked to show that they do not meet, I'm expecting to get a value which is different to minus 19 over 3 upon substituting the value we obtained for mu into 4 plus 9 mu. So let's see. We've got 4 plus 9 mu being equal to 4 plus 9 times 3, which is equal to 31. I need to state that minus 19 over 3 is not equal to 31, and therefore we conclude that the two lines do not meet. We are then told that the point C is on L2 where mu is negative 1, and we need to find the acute angle between AC and L2 in degrees to 1 decimal place. So what I will do, I will take mu is -1 and substitute into the equation for L2. This will give me the position vector of point C. So OC will be equal to 3, 1, 4 plus -1 times the direction of 1, 5, 9. This gives an answer of 2, -4, -5, which is the position vector of point C. And I can therefore proceed with a quick diagram to see exactly what's happening. We've got the line L2, we've got the point C somewhere along the line with coordinates 2, -4, -5. We just found this here. Somewhere off the line we've got the point A with coordinates 6, 6, 2, and we're trying to determine the size of the angle theta here. So I will start by finding the vector CA, which is equal to the vector A, 6, 6, 2, minus the vector C, which is 2, -4, -5. This gives an answer of 4, 10, 7. This is the vector CA, and I will proceed with the dot product between CA and the direction of L2, which is 1, 5, 9. This should be equal to the magnitude of CA times the magnitude of 1, 5, 9 times the cosine of theta. So CA is 4, 10, 7, dotted with 1, 5, 9 is equal to the magnitude of CA, which is 4 squared plus 10 squared plus 7 squared square rooted times the magnitude of 159, which is 1 squared plus 5 squared plus 9 squared. This is simply Pythagoras in 3D times the cosine of theta. Well, we know that when we are doing the dot product, we multiply the I with the I, then the J with the J, and then the K with the K, and we add everything up. So we're looking at 4 times 1, which is 4, plus 10 times 5, which is 50, plus 7 times 9, which is 63, being equal to root of 165 times the root of 107 times the cosine of theta. So on the left hand side we've got 117. I'll divide by root of 165 and the root of 107, and this is equal to the cosine of theta. And if I do shift cos of the left hand side, we arrive at theta being equal to 28.3 degrees. In 9a, we are asked to find the derivative with respect to y of 1 over 1 plus 2 ln y all raised to the power of 2. I will start by saying consider w to be exactly the expression in terms of y that I was given, which can be written as 1 plus 2 ln y raised to the power of -2. All I'm being asked to do here is find dw dy, so the derivative of this expression with respect to y. So I'll get the power down, I deduct 1 from the power, so 1 plus 2 ln y to the -3, times the derivative of the bracket. The derivative of the bracket, it's going to be 2 over y, and this simplifies to -4 over y times 1 plus 2 ln of y raised to the power of 3. In part B, we are asked to find the general solution to this differential equation here. I will start by separating the variables, which means I will be collecting the terms in y on the left hand side with dy and the terms in x on the right hand side with dx. So I'll be cross multiplying. So I get 1 over y brackets 1 plus 2 ln of y raised to the power of 3 dy is equal to 1 over 3 cosec of 2x dx, and I can integrate both sides. Well, I notice that the left hand side to be integrated looks very much like the answer we just obtained in part A. We're just missing the -4, so I'm saying it would be just great if we had a -4 here. So I'll multiply both sides by -4. So we're looking on the left hand side at the integral of -4 over y brackets 1 plus 2 ln of y raised to the power of 3 with respect to y, and on the right hand side we've got the integral of -4 over 3, and the 1 over cosec is simply sine, so sine of 2x dx, and this is exactly the moment I'll be using part A. If the derivative of this here is -4 over y, 1 plus 2 ln y to the power of 3, then obviously the integral will be the thing we started off with. So the left hand side will simply give me 1 over 1 plus 2 ln of y raised to the power of 2, while on the right hand side we've got minus 4 over 3. The integral of sine is negative cos, but I also need to divide by the derivative of 2x, so I need to divide by 2. So we've got minus a half cos of 2x, and we've got a constant of integration plus c, so I can simplify things. We've got 1 over 1 plus 2 ln of y raised to the power of 2 being equal to 2 over 3 cos of 2x plus c. In part C, we need to show that the particular solution of this differential equation satisfying that y is 1 when x is pi over 6 is given by y is e to the a sec x minus a half, where a is an irrational number to be found. Well, from part B, we have arrived at 1 over 1 plus 2 ln y squared is 2 over 3 cos of 2x plus c. The first thing to do is use the boundary condition that x is pi over 6, y is 1 to find the value of c. So when x is pi over 6, we get that y is equal to 1. Let's substitute. We get 1 over 1 plus 2 ln of 1 raised to the power of 2 is equal to 2 over 3 cos of 2 pi over 6 plus c. Now we are obviously in radian mode. On the left hand side, ln of 1 is simply 0, so the left hand side is simply 1, which is equal to 1 over 3 plus c, and therefore we conclude that the value of c is 2 over 3, and therefore we've got that 1 over 1 plus 2 ln of y raised to the power of 2 is equal to 2 over 3 cos of 2x plus 2 over 3. Now the next thing to do is express the right hand side over the same denominator of 3. So this is simply 2 cos of 2x plus 2 over 3. And then we can recall the double angle formula for cos of 2x. We know that cos of 2x is equal to 2 cos squared x minus 1. So I'll be substituting cos of 2x with 2 cos squared x minus 1. This leads to 1 over 1 plus 2 ln of y raised to the power of 2 is equal to 2 brackets 2 cos squared x minus 1 plus 2, and all of it divided over 3. I will expand the right hand side to get 4 cos squared x minus 2 plus 2, and all of it divided by 3. We can obviously see the negative 2 with the plus 2 cancelling out. So at the moment I'll be flipping both sides of the equation, leading to 1 plus 2 ln of y raised to the power of 2 is equal to 3 over 4 cos squared x. Well, we should be able to recognize the right hand side as simply 3 sec squared x over 4, and therefore I will proceed by taking the square root of the right hand side. This leads to 1 plus 2 ln of y being equal to root 3 sec x and all of it over 2, which means that we're looking at 2 ln of y is equal to root 3 sec x over 2 minus 1. I will divide everything by 2 to isolate the ln y term. So we've got ln of y is equal to root 3 over 4 sec x minus a half. And the only thing missing is to do e to the right hand side to get rid of the ln. So we've got y is e to the root 3 over 4 sec x minus a half.